Hello. All right. There she. Hello. Oh, there they. Okay. Hello, Lila. Hello, Mantra. Hello. Excuse me. Hello, Tania. Hello, Chen. Chen. Hello, Jadith. And now the chat. Good afternoon, Luis. Oh, here we go. All right. Good afternoon, Danielle. Hello, Tania. Hi, Lila. Oh, good. Thank you. Oh, good. Thank you for asking, Lila and Chen. And there's Raymond. Hello, Raymond. Hello, everybody. All right. First of all, yes, long time no see. I was just going to say that, Raymond. Exactly. And good afternoon, Camille. And thank you much. Yes. So it's been a really long time. It's driving me crazy, actually. And I'm sure it's driving you crazy in a different way. Yes, I really missed you guys. I'm doing very well. Thank you. I hope you're doing well. Um, Obviously, I'm looking more and more different every day. That's just the way it goes. It's freaking out my son, but my younger son. But no, I'm feeling great. Thank you for asking. I could be more detailed about that. Modern medicine is an amazing thing, and I'm very lucky. Blah blah blah. But um, but I miss you guys, and it's like to end all the holidays too are all confusing. So so I'm happy to be back in the saddle with you people, and we have lots of catching up to do physics wise. Oh, and there's Michael and there's Joyce. Awesome. Hello, hello, awesome. All right, this is like a full awesome. He even smiles. Okay, I mean everybody smiles. Okay, so no, I really am blessed. Anyway, it's I appreciate all the what I you know what I really appreciate more. Oh, sorry, this is nothing. What I really appreciate more people coming above everything that it is clear that you guys have been doing everything possible for you to stay on top of the work and the course material, even through all the holiday schedules and my funky schedule and everything like that. And it's yes, hello, Nico. It's very clear that you are staying on top of things as best you can, which I really appreciate. And I do notice, pardon me. So, um, and I know it's more gratifying for all of us to learn in a synchronized way, I think. But you've had a lot of unsynchronized learning, and I can tell from the video comments and stuff like you're making it very you're making it easier on me to know where we need more reinforcement and where I can save time by not being redundant. Um, wait, more people coming. Okay. So, and it should be normal class this Wednesday, right? Like Wednesday's a regular schedule for John Jay and for me. Okay, thank you, Lila. Okay. So yeah. So we could start getting momentum again here. Um, so I'll show you what we're gonna do what we're gonna do today is I'm gonna sort of blast through the key highlights of where you've been in the material, like through the videos and everything. In other words, I'm not gonna redo each of the classes of the video, but I'm going to do the major beats, the major highlight concept that has occurred since we last met in a synchronized way. And I'm going to encourage you as I go through the major beats for you to stop me and say where you still have issues, if I don't explain it right then. In part, I'm doing this in recognition of what you all told me in the video prompt responses. There's some confusions that I will explicitly address. I know in advance, but you stop me. So this is like a catch-up day intellectually, if that makes sense. We're going to try to catch up with ourselves with the material. And the ultimate goal is to get to the point of understanding all this Doppler effect business. That's the ultimate goal. Now, I've been sort of funky with the homework assignments. Like the Doppler effect was, in theory, was due either today or last Wednesday or something. And tons of you turned it in, and you'll see, and tons of you got points and some feedback, some quick feedback. Let me make it clear. First of all, again, if you handed in any draft of the Doppler effect at all by the time that it was due, then you certainly still can get all the points. And any points that you didn't get or anything that I said as a criticism, I mean, is not a criticism. Like, I know that you started that. We haven't said anything about the Doppler effect in this class. That was a big reach forward for you to attempt to do on your own without any explanation. I'm fully aware of that. So again, whatever points you got is in recognition of you made a valiant first attempt, and now you still can get all the rest of the points. I think that's clear. So more specifically on the Doppler effect, which is our goal to get to, many of you used an equation there to do your calculations, and presumably you got the equation from the web or maybe from your lab professor, but I'm assuming from the web. I'm not saying it's not illegal to use the web, and especially if no one's explained anything. I mean, what are you supposed to do? Of course, you can go on the internet and try to figure things out. And that equation that many of you used, you may have noticed that I wrote www next to it, which means what, where, from, why, or what, why, where, from. Or I wrote something like the equation is unwarranted, or there's no warrant for this equation. And let's be very clear about this. I'm not saying you cheated at all. I'm not. I'm also, I mean, certainly you're not cheating by going to the web and getting equations. Second of all, I'm not saying the equation's wrong. It's not wrong. And again, I'm also not saying that you're being penalized or something like that. Like what I am saying is I have an issue with that equation, and you couldn't have known that necessarily, or you know, so eventually you'll get all the points once you do it a different way. But let me make clear a couple of things about warrant and www and stuff. For when we eventually get to a midterm exam, which we're soon going to start talking about and scheduling and all of that, you can always get anything you want. You can get any help from other people, from other students, from the MSRC, from the internet. You can always get help anywhere in terms of explaining things. But by the time you write something down, especially on an exam, it has to be justified and explained, which ultimately means it has to be justified and explained with regard to, with reference to, or from whatever general definitions and principles we've established in the class. Now, again, right. So what I am saying is, just in terms of practice for an exam that we eventually have to take, by the time we get to an exam, that equation, and if you don't know what I'm talking about in terms of the Doppler effect, then don't just take this as a general comment. That equation that many of you use that has two V's in the numerator and two V's in the denominator, like if you were to, I want to warn you that if you were to use that, that is not a fundamental equation. Like that's not a definition. It's not a concept. It doesn't in and of itself make any sense unto itself. It's a shortcut that comes from putting together a bunch of other equations that make sense. Once somebody understands it, once you know where it's coming from, if one can explain it or derive it once and then use it as a shortcut, that's fine. But it can't be a starting point. In other words, what I'm really saying is that equation, the Doppler effect equation that you get from the web, is not a general definition or principle. Like you can't start things with it. It's not a step 3. If you're going to use it, you really have to explain it. And I'll even warn you, you'll see when we get to this, the exam is designed to ask when you get to the Doppler effect part of the exam, and we will exam, it's designed so that a bunch of questions are asked about a Doppler effect situation that literally can't be answered directly with that equation. So once we get to this, I know I'm all over the place already, but once we get to specifically talking about the Doppler effect, you're going to want to be able to break it down and understand it conceptually in terms of physics ideas in a way that's more fundamental than that equation. That is just a caution that I'm saying. And in general with exams or future homework and stuff, just always real any equation that you ever write down, if you get it, if you don't think it came up in class, if it's coming from the web or somewhere else, that doesn't mean it's wrong and it doesn't mean you can't use it, but it means you better go to extra effort to make sure that you see how it connects to the material of class and you break it down into step 3 GDPs that way. I sort of hope that makes it. So be on the lookout when we get to the Doppler effect to see what I'm talking about. Now, again, none of this is a criticism or a punishment or anything like that, especially because I'm aware that you started that Doppler effect homework way before we said anything about waves at all. So what were you supposed to do? Like, I get it. Like, even if you do it the right way that I'm going to teach you, you still, even the way that I'm going to teach you, you couldn't have really understood, known before, like now. So that's also the reason I want to say that that Doppler effect homework, not only is everybody still going to get a chance to get all the points, but in fact, I technically even extended the deadline to this Friday. So we're gonna catch up on material today. Then we're gonna get ourselves back into the seat of waves, which is really the concept now. And then we're going to talk about waves in more detail on Wednesday. So really, by the end of Wednesday, you should have a much firmer grasp of what I'm actually looking for in this Doppler effect thing. So then, even though we don't have class Friday or anything like that, I'm just saying you have a re-extension till Friday to do the Doppler effect fully, thoroughly, so that you just know that I know you're ahead if you're already worried about the Doppler effect. Okay, I hope that sort of makes sense. But now, the 23rd. Oh, did I? The 23rd. Oh, the 23rd is in 2 days. Oh, I thought I just changed it. It was, no, you're right, but I thought I meant to just change it like 5 minutes ago. Wait, let me see if I did. No, I think you're, if I didn't, I'm going to do it right now. Thank you. I don't even know who wrote that in the chat, but I'm guessing it might have been Michael. Hold on. Yes, you're right. It was the 23rd, but I think as of about 20 minutes ago, I think I changed it to the 25th, which is this Friday. And in fact, I'll even to make it more clear, it says 3:05 p.m., but that's weird because it's not like we have class that day. So I'll make it midnight just so it's super clear that this is like a extension kind of thing. Okay, so that just changed. Oh, okay. No, all right, and now it says this way. Okay, great. And it was Michael. Okay, no, great. I'm glad you guys pay so much attention. No, you're all on top of things. I hope it's clear. You are doing a great job of staying with this material, even when it's not being explained in synchronized manner. Okay, and okay, thank you both. You could submit for points, blah, blah, blah. All right. So now what I'm going to do, and again, I feel like I know not only what you were meant to watch in the videos, but I feel like I know from your feedback to the videos kind of where things are somewhat clear and where they're somewhat fuzzy. So I'm going to do this in, sort of big bullet points. In theory, this is now like, scenes that we've missed since we've been gone. But you stop me. Use this especially if it looks like I'm about to go on to a next thing and you don't like the last thing I just said, stop me. So here we go. And I'm going to switch. Okay. Let me just change the view here. Okay. Okay. Yep. Okay. First thing, so again, this is going to go a little bit maybe fast. I'm going all the way back now to like homework 1 and homework 2, trying to say, and then in homework 3, because I know we never talked about homework 3, but it seems like a lot of you got homework 3 pretty, and we never finished homework 2, but it was all in the videos. So I'm just like this is like summarizing homeworks 1, 2, and 3 here in bullet points. So first of all, it all started, if you have a mass going back and forth on a spring, um, it can, the Hooke's law situation can be described by this differential equation. Okay, in other words, Okay. So the first thing that was sort of we were spending all that time on homework 1 and homework 2 kind of establishing is that if there's some variable y, like it could be x, it could be, we call it z, sometimes I call it z. If there's some measurable variable that depends on time, so let's call it y right now. If the dependence of y on t can be described by that differential equation, that second order differential equation. In other words, if the second derivative of the sorry, someone's here. If the second time derivative of some dependent variable is equal to -1 times some constant, some positive constant, times the variable itself, right? If the rate of change of some measurable dependent variable is found to be directly proportional to the variable itself, right? That's what that differential equation says. Then that variable is oscillating harmonically in time. Then the value of that variable can be described by a cosine function that is wiggling back and forth at a certain rate. At a certain rate that is constant. The rate at which the cosines wiggle back and forth, the rate at which cycles occur per time, we call angular frequency, we call omega. And we say that any variable that can be described by that differential equation is oscillating harmonically in time, is oscillating cosinusoidally in time at a rate that is constant. And that constant rate is the square root of whatever the constant is in the differential equation. There's a lot of information in what I just said, but that's sort of the summary of homework 1 and homework 2 and homework 3. Tell me if I need to go back, but I'm going to expand on that for a second. So someone specifically asked, well, more than one person specifically asked about this in one of the video postings. Like, so an example, like where this all began was in the case of a mass on a spring, where the spring had a stiffness of K and the mass was a mass of M. And the mass was going back and forth along an x-axis. Like I just changed the y's to x's. I'm just making a specific example here. And I changed the omega to K over M. I'm saying like, the point is that if you know that this differential equation applies to the variable x, if you know that the second time derivative of x equals -1 times some constant, which could mean some combination of constants, times the x itself, then you know that the value of x is following a cosine function, is wiggling back and forth at an angular frequency, which is necessarily the square root of whatever that constant is in the differential equation. So in other words, originally this all started with K's and M's. But what we're trying to say with homework 1 and homework 2 and homework 3 is it doesn't matter if it's actually literally like a block of mass on a metal coil. It doesn't matter if there's literally a spring with a stiffness constant K or literally a mass with a mass of M. The point is any value that obeys any variable that obeys this differential equation will act like a mass on a spring, will oscillate back and forth just like a mass on a spring does. That's why this whole course is sort of based on a mass on a spring. Anything to which this math applies, the math fully applies. So even a pendulum bob on a string going back and forth where the variable is not x, but the variable is theta, or a temperature system like homework 3, where it's neither x nor theta, it's like temperature going, hot and cold and hot and cold. As long as the differential equation describes that variable, then the variable will oscillate cosinusoidally at a rate that is necessarily the square root of whatever the constant is in the differential equation. And you might say, well, how do I know that there is a constant in the differential equation? If there isn't, then it's not what we're talking about. Like the requirement of this whole thing is that the differential equation, the type of differential equation we're looking at right now, says second time derivative equals -1 times constant times the original dependent variable, right? So yeah, I'll just leave it like that. So the omega, the angular frequency for any oscillator. So again, this is like reviewing now. I'm going to move on in a second, but just like the highlight. So mathematically, sorry. Well, okay, no, I'll say this. I'm saying anything that obeys that differential equation. And what is that differential equation? Really, it's the mathematical way of saying Hooke's law. That's where we got it originally. We put F equals negative KX into F net equals MA. So anything that mathematically acts like a spring, physically acts like a spring, anything that can be described by this differential equation, any variable that can be described by this differential equation will oscillate back and forth in the manner of a cosine and will oscillate back and forth at a rate that is the square root of the constant in the differential equation. Now, the rate we call angular frequency. Angular frequency is number of radians that we traverse, that we accomplish every second. Now, many of you are asking good questions about like, wait, so how does radians have to do with like a mass going back and forth on a spring? The quick version, I mean, I know I talked about this in the videos, but the quick version is like radians are coming up, not just because cosines are coming up, but because a radian is a measurement of angle, and an angle is a fraction of a circle. And all of this the physics that we're doing, what we're doing is we're taking the mathematics that we already have for circles and we're grafting those mathematics onto the physics of cycles. What we're saying is an angle is a section of a circle. Like, I don't, whether you call it 90 degrees or pi over 2 radians or whatever, everybody recognizes 90 degrees. Everybody recognizes, or you call it a right angle. What is a right angle? Everybody can, I can never do it on the backwards mirror, but a right angle, everybody recognizes as a right angle, the thing that looks like a perfect L, which I'm not doing. Everybody recognizes a right angle. And the thing that you recognize about a right angle, notice, it doesn't matter how big my arms are. Like my fingers could extend all the way there to all the way there, or it could be really short, and you would still recognize it as a right angle. Because what you're recognizing as a right angle is that it is a fourth of a circle. Or just like my 10-year-old son knows 360 no scope. He knows a 360-degree angle. He knows it means a full circle. Therefore, he knows a 180-degree angle is a half a circle. Now, he doesn't know radians. That's a different way, but it's the same idea. What he's recognized, what he understands, what we all should understand is that angles are sections of circles, and we recognize the size of the angle regardless of how big the circle is. That's the whole point. That sections of circles fractions of circles are universally recognizable and identifiable regardless of how big the circle is. Same thing with cycles. So if there's 2 pi radians to a circle, which is the one thing, if you're confused about radians, memorize this. A full circle is 2 pi radians because the circumference around any circle is 2 pi r. Again, saying it doesn't matter how big the circle is. It's always 6 times longer to go walk around the whole circle than it is to go from the center to the outside. That's what the 2 pi means. I mean, a little bit more than 6, right? Like, it's not important what the number pi is. It's important that it's a constant number. That it doesn't matter how big the circle is. It takes the circumference is always 2 pi times greater than the radius. So one cycle is 2 pi radians. That means, that means 1 radian is 1 2-pith of a cycle, of a circle. In other words, a radian is approximately 1/6 of a cycle. That's what you just want to remember. If nothing else, where did I get 1/6? I'm rounding 2 pi to 6. I'm saying there's a little bit more than 6 radians to a circle. A radian's a little bit less than 60 degrees, 57 degrees, right? So what a radian is a little bit less than 1/6 of a circle. What that has to do with anything is that we're taking the mathematics of circles and saying that can be applied to cycles. A radian is like 1/6 of a cycle. So when you talk about omega, you're talking about how many cycle sixths an oscillator makes per unit time, per every second. Would it be easier just to talk about how many cycles it makes per second? Sure, it would. That's why you can convert angular frequency omega to standard frequency f. If you know the angular frequency, I'm doing this fast because you've seen this before, but I'm just trying to put it together. If you know the angular frequency of something, if an oscillator, if this mass going back and forth on a spring has an angular frequency of 2 pi radians per second, that sounds as obscure to me as it does to you. It doesn't sound like it means anything. It has an omega of 2 pi radians per second. What does that mean? What we're just saying is it's doing 1 cycle per second. If you literally just divide omega by 2 pi, you get this thing called f, standard frequency, the much more natural thing to think about, just the less mathematically convenient, but more natural thing to think about. If you divide angular frequency by 2 pi, you get standard frequency in units of straight cycles per second. 1 cycle per second is called a hertz. If you've never written that down before or never heard it in a video, write it right now. Like 1 cycle per second is called an HETRZ, a hertz. So if something, so let me be more clear or more practicey. If I say that an oscillator has an angular frequency of 4 pi radians per second, 4 pi radians per second, what does that mean? It means every second it's doing 4 pi radians. There's 2 pi radians to a cycle. So divide in your head by 2 pi. If something has an angular frequency of 4 pi radians per second, then it's doing 2 complete cycles every second. It has a standard frequency of 2 hertz. What does that mean? It means it takes a half a second to complete 1 cycle. That's the last bit here. Like I'm saying, to go from angular frequency to standard frequency, you divide by 2 pi. To go from standard frequency to period, to amount of time per cycle, you invert. You take the reciprocal. Like standard frequency is cycles per second, period is seconds per cycle. So if something, I'm just going to say it one last time, and then I'm going to move on just to try to. If something has an angular frequency of 4 pi radians per second, then it has a standard frequency of 2 hertz. And that means it has a period of 1/2 second per cycle. If you know one of those 3, you automatically know all 3. They are 3 different ways: angular frequency, standard frequency, and period. 3 different ways for measuring the same information, which is cycling rate. The reason we have 3 different ways to measure the same thing is angular frequency is what comes out most directly and conveniently from the math. Period is what comes out most naturally and visually in the lab. Period is the easiest thing to measure, the easiest thing to picture and visualize in our mind for all of us. How many seconds it takes to do a cycle is the easiest thing for all of us to relate to. Angular frequency is the hardest to relate to, but it's the most mathematically usable. Standard frequency is the bridge between the two. So that's why we have the three. Okay, so if you know one, you can get the other two. Bottom line for all of this, very quickly now, this is a huge point, the conceptual point that I'm about to say. I don't want to dwell on it now because it won't help you with, well, I just want to remind you who's in the videos and everything. Anything that goes back and forth, anything that undergoes cyclical, periodic motion, it can be called oscillation. But everything that we've been talking about in homework 1 and homework 2 and homework 3, all of that is specifically called SHO, simple harmonic oscillation. Now, what is this word harmonic? And from here on in, like every time we're talking about oscillation in this class, we're talking about a specific kind of oscillation known as harmonic oscillation. What do I mean by that? The oscillation part just means that the motion is periodic or cyclical. To say that these oscillations that fit the differential equation, to say that they are harmonic is to say that the cycling rate, the angular frequency, is so constant, like it's a constant, right? It's the square root of whatever constant is in the differential equation. The angular frequency is a constant. It is so constant that it is not a function of the amplitude. You see what I'm writing here at the bottom? I'm saying the angular frequency is a constant. So you could even write like this, like angular frequency is a constant, and it is not dependent in any way on the amplitude, on the initial value of the independent variable. Well, yeah, I can't write it any better than, I mean, I could, but I'm saying no matter how you set up the oscillator, no matter how far out you stretch the mass on the spring initially, whether you started at 15 centimeters from the equilibrium or 30 centimeters from the equilibrium, 45, whatever, or if it's a pendulum, whether you started at 15 degrees or 20 degrees or whatever, within reason, no matter how you set up the ingredients of your oscillator, the oscillator will cycle back and forth at a rate that is fully determined by the parameters, by the ingredients of the system. Like if it's a mass and a spring, it only then omega only depends on K and M. It doesn't depend on X naught. Or if it's a pendulum, omega only depends on G and L. It doesn't depend on theta naught. So harmonic oscillator is an oscillator that cycles at a rate that is independent of conditions, dependent only on parameters, dependent only on the material properties of the system, not on the way that you set the system up. Okay, that's a summary of one big point from homework 1, 2, and 3. Again, if you have issues, like jot them down or text me or, but okay. Now, so that's like one big beat. So then you were practicing with the differential equation and stuff like that. But then you find somewhere in the middle, so that's like beat one. Well, I'm just gonna keep going. Then you find somewhere in the middle of homework 2, you find right? What we find in the middle of homework 3 is that actually the A cosine omega t or x naught omega or y naught cosine omega t, like that is a solution that describes a simple harmonic oscillator. But actually, it's not the only solution. We could add a constant term to the piece in parentheses, the piece that we're taking a cosine of. We could add any kind of constant number to the cosine argument. And if we differentiate it twice, we still get back the original differential equation. So apparently, like, we don't have to assume that there's a zero being added to omega t to make this work, right? And we find that we can add any kind of, well, yeah. You can add any kind of term you want, any kind of constant value to that parentheses. And as long as it's measured in radians, you'll still be describing a simple harmonic oscillator we found in the middle of homework 3. And that term that you could add there is called a phase constant. Um, Okay, I'll get you 1 second. Okay, wait, someone's here. Okay. Okay. So just quick example. So now I'm treating my dependent variable here as y. So in my mind, I'm picturing, it could be anything, right? I mean, when the whole semester started, we were talking about x. Now I'm talking about y. Because I'm picturing a mass that's on a spring that's vertical. I mean, I could picture whatever I want, but it'll be useful for me to picture a mass on a spring that's vertical. So it turns out that I could put in this term called a phase constant, and the phase constant measures a head start or a delay with regard to phase, with regard to portion of cycle. Like, again, phi, for this math to work, phi, this Greek letter phi, has to be measured in radians. Otherwise, you couldn't add it to omega t. Omega t is already in radians, right? It's radians per second times seconds. So you can't add anything to radians but more radians. So phi has to be measured in radians in order for that whole parentheses thing to be in radians and for us to take a cosine of it. So whatever phi, the phase constant is, it's something measured in radians. A radian is a portion of a cycle. So the phi is measuring where we are in the cycle when we start our stopwatch, when we start counting cycles for this oscillator, like if we were in the lab or whatever. In other words, and again, it's measured in radians, right? So for example, in all the, sorry, no problem. Got you, direct chat person, thank you, no problem. So what phi is doing, just quick example again, in principle, you know this, but I'm just reviewing. Phi, we got away with not even thinking about phi, without even thinking about the phase constant for the first couple of homeworks, because we were tacitly treating phi as zero, without even thinking that that's what we were doing. And what does it mean when phi is zero? It means we're plugging in zero there, so that whenever t is zero, just plug it in your mind. When t is zero, anything times 0 is 0. The cosine of 0 is always 1. 1 times A is A. So when phi is 0, that means there's no head start or delay in the phase. It means the experiment started, or we started paying attention to the experiment at the most natural place possible. We were like, the thing was going back and forth and back and forth and back and forth, and we started our stopwatch the moment we saw the mass get all the way to an endpoint, like right as it's coming and coming out, it's slowing down. Now it stops, so it's an easy moment to start our stopwatch, and now it starts going back in the other way. That's the most convenient, natural thing to do, is to start your stopwatch when the object is at its amplitude position, or that's what happened in homework 1B. We started paying attention, V naught was 0, when the object was released from 15 centimeters away from the equilibrium, right? So when phi is 0, that means there's no head start or delay. The object was at a turning point, at a maximum, an amplitude, when the stopwatch started. That's if phi equals 0. However, if, for example, if phi were pi over 2, if the phase constant is pi over 2, what does that mean? It means pi over 2 radians. What does that mean? There's 2 pi radians to every full cycle. So if you have a phi of pi over 2, that means that the object is already a quarter way into its cycle, or a quarter way back from its cycle, when we started our stopwatch. Where did I get a quarter? Because there's 2 pi radians per cycle. So pi radians is, so 2 pi radians literally means there and back, like all the way there, all the way back. That's what 2 pi radians means for an oscillator. All the way there, all the way away to the other side, and all the way back. What does pi radians mean? It means half of that, just all the way there. What does pi over 2 radians mean? It means halfway there. It means from an amplitude to the equilibrium, right? So if you say an oscillator has a phase constant of pi over 2 radians, it means it was already a quarter way into its cycle when you started the stopwatch. It means it's already at equilibrium when you started your stopwatch. If you just do, that's what it conceptually means. And look at the math. If you plugged in pi over 2 radians for phi here, if you plug in your mind, plug in pi over 2 radians for phi, and ask yourself, what's the value of y? What's the dependent variable? When t equals 0, right? Well, t equals 0, anything times 0 is 0. So 0 plus pi over 2, we'd be taking the cosine of pi over 2, the cosine of pi over 2 radians, think of the unit circle, the cosine of 90 degrees, the x value of the top of the unit circle is 0. In other words, if you just plug in, to have a pi over 2 phase constant means that the object was already at 0 at the equilibrium position when we started our stopwatch. Okay, so that's just again. Good. Someone's in the chat. Good. Wait. Yes, exactly. So someone just put in it. Perfect, beautiful. You should submit for points for that. So someone said in the direct chat, I'm just going to repeat it without the name because it's good. It's right. They said, so are you, excuse me. So am I, thank you. Awesome. Now you just got more points for awesome. So am I saying that since it's already in motion, like if the phase constant is not 0, then am I saying that since it's already in motion, it's already at equilibrium when it starts, so y has to be 0? Yes, I'm saying, yes, I'm saying if the phase constant is not 0, that means the thing was already in motion when we started our stopwatch. That's correct. And specifically, if the phase constant was specifically pi over 2 radians, then specifically the thing is exactly at 0 when we started our stopwatch. I mean, if the phase constant were something else, say the phase constant were pi. I mean, it could be anything. If the phase constant were pi, that would mean it was all the way on the other side when we started our stopwatch, like half a cycle on the way in. I hope that doesn't confuse you further. I hope, but yeah, so yes. Now, so that's the idea of the phase constant. That sort of comes out of problem 1F in homework 2, when they just add the number 3.5 and ask you to take the derivatives, and you notice that the chain rule doesn't affect the number 3.5. Anyway, so that's the idea of a phase constant. It's where you are in the cycle. Okay. Whoa, okay. Great. No, I'm glad the person just followed up. So apparently I am making this harder. Okay, so the person in direct touch just followed up. So, right. So if the phase constant were a different example, if the phase constant were pi, then at t equals 0, y would be negative a. Let me show you what. First of all, okay, so it wouldn't be 0. So it's a great question, but the answer is no. Like the person just asked, so wait, if the phase constant were pi, would y still be 0? And I'm saying, great question. You're definitely following me. Yeah, it would be easier. Right. I'm just trying to go a little. I may draw something in a second. Right. So someone else just suggested very correctly that if I would stop and draw a cosine graph, it'd be easier for people to see. And I do agree, and it's a great suggestion. I'm just a little worried of me rabbit holing myself, like starting to draw things and then getting bogged down. So I may not do that right now, but it's still a great suggestion. You should still submit that for points. Or if someone wants to in the, but just see if you can follow this for a second. I'm saying conceptually, if the phase constant is pi, the key thing to all of this is 2 pi radians equals 1 cycle. Like that's what you want to remember for all time. Therefore, pi radians equals a half a cycle. Like 2 pi radians means there and back. So if the phase constant is pi, it means the thing is already fully there, but not back when I start my stopwatch. So if it's already fully on the other side when I start, like if it's 0, if the phase constant is 0, it's if the thing started, the thing was at amplitude when I started my stopwatch. If I wait half a cycle, then it's all the way on the other side when I start my stopwatch. So conceptually, I think y would be the value negative a at t equals 0 if phi equals pi. He's probably right. I probably should draw something in a second, but but just plug in also. Like, look at the equation right here, the white equation at the bottom of the board. Like, if, right, right. I mean, just literally plug in right here in your mind. If you plug in, we're trying different values. If you're trying to understand the phase constant is telling you where the thing was at t equals 0. This is always about where is the thing when we started timing. So for this, I'm not saying t is always 0 in life, but for this context that we're discussing right now, we're trying different values of phi and seeing what impact they have on y at the moment that t equals 0. So if you plug in pi for phi, now plug in your mind 0 for t. 0 times anything is 0. 0 plus pi is pi. The cosine of pi, maybe this is where the graph could come in helpful, or maybe you can draw a graph for yourself if it's helpful. Cosine of pi means cosine of 180 degrees. Go to think of the unit circle. Cosine of 0 is 1, but cosine of 180 degrees, like the other side of the unit circle, is negative 1, right? Cosine of pi is negative 1. Negative 1 times a is negative a. I'm saying, and then I will move, even if this is, let this sink in and think about it on your own because I think the questions are really good. But I want to make sure to get to some more stuff too. So, go. Okay, great. Awesome. Thank you. Okay, awesome. So I'll finish the thought just for everybody. So I'm saying, you'll know you understand the phase constant if you can see that, yes, for example, these are just examples. But if the phase constant is 0, then y equals a when t equals 0. If the phase constant is pi over 2, then y equals 0 when t equals 0. If the phase constant is pi, then y equals negative a when t equals 0. If that's a jumble, write it down and think about it later and come to me later. But that's the basic idea of phase constant. The phase constant is where the thing is when you started measuring its cycles. Now, what you might be thinking, if you're sort of following this, something that might be confusing, I'm going to move on now, but those are great questions though. What might be confusing you is you might say, but okay, I sort of get it, but like, why are you making things hard, Yaverbaum? I mean, like, if it's easiest just to measure the thing, an oscillator, if it's easiest to start your stopwatch when the oscillator is at amplitude, why would you ever do anything but that? Oh, good. I'm very glad. Thank you for all the, there's a lot of things happening in direct chat and it's really helpful. I appreciate the feedback and so good, good. You might say, not that anybody might say, okay, I get it. Like I get the math, sort of the plugging in, or I am drawing constant graphs and I see them. But like, why are we bothering? Like, why would we not just always start our stopwatch when when the oscillator is at an amplitude position? Isn't that the easiest place to start our stopwatch? And isn't the math easiest when we just don't even have a non-zero phase constant? Yes, yes, yes. If you're thinking anything like that, you're correct. The reason, so in short, if you only have one oscillator, which was the case for homework 1, homework 2, and homework 3, we're always only studying one oscillator in those and for the first 2 labs. You're only studying one oscillator, whether it's a mass on a spring or a bob on a string. The first 2 labs and the first 3 homeworks, we were looking at a harmonic. In fact, let me write that clearly because this is where people got confused in the videos and everything. So I'll write this. We were studying one simple harmonic oscillator. Please write it out if that's it. One simple harmonic oscillator. And when you're studying one simple harmonic oscillator, you don't need to worry about the phase constant. It is stupid and annoying. If you just have one oscillator, you might as well start the oscillator. You might as well start your stopwatch when the oscillator is at an amplitude position, and you don't have to worry about the phase constant. And that's why we didn't worry about it for all the problems we were doing originally. However, okay, at some point, essentially in lab 3 and correspondingly homework 4, at some point, all of a sudden in this class, we started talking about waves. Now we didn't really because you in lab started all of a sudden thinking about waves. And then the videos started talking about waves. And of course, that's huge to the class, waves. What we really care about in this class is waves, which are unthingy things. They are huge and super important central topic to this class. But let me make very clear right now where people get confused is we weren't talking about waves until we were talking about waves, or we weren't studying waves until we were studying waves. All this stuff from the first 3 homeworks and the first 2 labs, those are simply oscillators. They are not waves. They're not wave equations. They're not wave motions. There's no waves in the first 3 homeworks or the first 2 labs. It's very important. One mass going back and forth on a spring is not a wave and cannot be described by a wave equation or anything. It's an oscillator. It's one oscillator. It's a thingy thing. What happened at a certain point between lab 3 and also lab 4, if that's what you're up to now, and various videos, what happened, and I'm going to say this quick, like this part is hard and it's deep, and I'm going to summarize it very quickly right now. You're going to have to sort of rewatch videos to get this straight, but we eventually asked you to picture. We said if you take a bunch of vertical oscillators and you lay them out next to each other horizontally, so something like this. et cetera, et cetera. If all of so you have a bunch of vertical oscillator, and they could be hanging from the ceiling or they could be sitting on the floor. I mean, it doesn't matter, but assume that all of these things are identical oscillators, that identical parameters, identical masses, identical spring stiffnesses, and they right? And assume this is that's a positive y-axis, that's a positive x-axis. Right? So assume that you take a bunch of identical oscillators and then you lay them out on a different axis and you spread them out equidistantly. So like the 0th oscillator is right on the y-axis and the first oscillator is on at 1 centimeter or 1 meter or some kind of unit of length. And then the second oscillator is at 2 units of length from the y-axis, etc. So you lay them out in the simplest possible way. Now, here's the key. I know, and again, you should rewatch the video where I really explain this because it's important. It is usually a test question on the exam. Like the key here. So now I'm saying once you understand what phase is, once you understand that phase is where an oscillator, like where in the cycle an oscillator is when the stopwatch hits a certain time, it's important for comparison. The reason phase becomes important is now, if we have many, many oscillators, imagine arranging them in the simple, all identical in terms of their material properties, i.e., all of these oscillators, that they have the same K and they have the same M. We can believe that they're all going to oscillate at the same omega. They're all going to go back up and down at the same cycling rate. Whether you measure that in radians per second or hertz or seconds per cycle, they're all going to do the same dance at the same rate, right, in time. But if we deliberately stagger their phases or stagger them in phase, like the first one might be at the amplitude position when we start our stopwatch, like the very convenient, obvious thing to do. But we deliberately now set the next one not to be in the same place. Like it doesn't start from the same place in its cycle. And the next one doesn't start at the same place. This is where we have to keep track of phase constant because we're going to deliberately give each one a different phase constant to watch the phenomenon as it unfolds. And let's do the simplest possible thing with this already complicated arrangement. Let's stagger their phases, but by a constant step, right? This is what the other video is trying to explain. Like, like, like the right? For example, and I'm taking too long with this, if each one were out of phase by another, like, so the first one's not out of phase at all. The first one has a pi over, has a 0 phase constant. Then the next one, let's say, has a pi over 2 phase constant. So it's at equilibrium when the first one's at amplitude. Then the next one, let's say, is at negative amplitude. If each next one is out of phase by another pi over 2, if you were to write a separate equation for each one of these, separate equations for each one would look something, in this example, would yield something like this. Like the very first one would be y equals a cosine omega t plus 0. That would be the 0th oscillator. The first one would be y1 equals a cosine omega. And remember, all the a's and the omegas would be the same because they're the same masses and the same stiffness. But y1 would be a cosine omega t plus pi over 2. The next one would be a cosine omega t plus 2 pi over 2, et cetera, right? Hopefully you see what I'm doing. Each one could be described by its own. Yeah. Oh, very good. This is like what we did in lab 4. Awesome. Wait. And yes, great questions. Sorry, and I know I'm going a little, but yes, what I'm doing right now is in effect what you were doing in lab 4. Very good. Yes. And also direct chat. So in lab, once you're in lab 3, you can start discussing waves in your post lab. Yes. Not before lab 3, but yes. Well, yes. So in effect, what I'm doing now is, yes, in a way, I'm jumping to lab 4. I'm saying lab 4 is where you put together waves from a collection of individual oscillators. Oddly, lab 3, you're looking at waves, and you're really, what's happening in lab 3 is you're looking at waves for the first time. You are looking at waves in lab 3, but you're investigating them so closely that once you really understand what's happening, which takes a while, you realize that you're dissecting waves into their individual cosine functions. You're pulling apart waves and seeing in lab 3 that a wave is a superposition of oscillations in time with oscillations in space. So in a way, lab 3 is weird because you're going backwards. You're looking at waves and pulling them apart and seeing, oh my God, waves are made up of multiple oscillations. And then once in theory you see that, then in lab 4, you go back and try to build a wave out of the multiple oscillations. What I'm trying to say, and I'm still going to continue this, but the big punchline that I'm trying to say is an oscillation is not a wave. A wave is a combination of many oscillations. You need to have oscillations to make a wave. You need to understand oscillations to understand waves. But that's the direction it goes. All waves consist of oscillations, but not all oscillations are waves. I hope that makes some sense. That's what and a lot of people seem to be a little confused about that in the homework. So that's what I'm trying to say right now. But now where I'm going with this, how does this lead you to like the wave equation or to the Doppler effect or any of that stuff? Because this is just an example right here. I mean, what's an example about this is the value pi over 2. That's just an example. The value of the step could have been anything. But if you look at the pattern of what I'm saying each individual oscillator has the same equation as every other oscillator. The only thing that's differing is their phase constants. They're all the same oscillator, but with different phases. But the phases are changing. The phase constants are changing in a certain pattern because that's how we set up the physical oscillators. So we could combine all these things into one big equation. We could say, like in this particular example, the whole collection could be captured in this example, where pi over 2 is the step. We could say all the oscillators together could be captured with the equation, with this equation. Right, in this example, right? Because if you look at it, when x is 0, then phi is 0. When x is 1, phi is 1 times pi over 2. When x is 2, phi is 2 times pi over 2. Because on purpose, we're just saying we're always increasing the phi by the same amount for every meter that we go across the collection. So in this example, we could say the whole thing is captured by omega t plus pi over 2x. But But in general, this step could be any value, any constant value, of radians per meter. Where did I get radians per meter? Because, well, first of all, look, X is measured in meters. If you want the thing, like, and remember, phi was supposed to be measured in radians. Like this term, this phase that we're adding on, this is just a rule here for whatever we're supposed to add on for any individual oscillator to tell us where it is in its cycle. The add-on term in the parentheses has to be measured in radians. So if X is measured in meters, then this term right before the X has to be measured in radians per meter. And what am I saying? I'm saying this pi over 2 was how many extra radians we were adding in phase for every meter that we went across the collection, right? That's what it is. It's a step. It's a phase constant per each next meter that we go across, or per each next oscillator that we look at, right? So we give this thing a letter in general. It could be anything. It doesn't have to be pi over 2. We call it K. Now, it's unfortunate that it's K again. It's just a bad coincidence. So I put serifs on the K just to distinguish. It's not the Hooke's law. It's not the K of Hooke's law. It's just a bad coincidence. So whatever, I put serifs on it. And we say from now on then that K equals, from now on, we're going to say angular wave number. The units of K necessarily are radians per meter. Okay, K stands for how much extra phase each next meter gets in the, how much of a head start or delay each next oscillator in this collection is given. But so the whole equation in general becomes this equation. So if you have a collection of oscillators staggered in phase this way, if they're phase staggered in a constant way like this, this whole thing can be summarized, like the whole collection can be written like this now, where, oh yeah, go back. Yes, sorry, like this. And I'm watching the, tell me when I can. And tell me when I, great, okay, thank you, awesome. And you submit for points for that. Okay, I'm saying, this is now a very big deal. I'm saying once I write this equation down, now again, I know I'm going faster. I'm just trying to summarize everything. And if nothing else, just use today as an opportunity to see where you need more help or where we need to discuss more or whatever. But once I write this down, now that y is a function of two independent variables, t and x, now this is this is many, many, many oscillators next to each other arranged in a very specific way. And if you stand back, the whole point is if you make this in lab 4, what you find is exactly what you see from the start in lab 3, whether you knew what you were seeing or not. If you look at a whole bunch of oscillators and they're all going up, down, up, down, up, down, but they're all out of phase this way, they're all staggered in phase in this constant way, then the first one goes up and then goes down, the second one goes up and then goes down, the third one goes up and then goes down. And what you see is a wave rippling across. Hopefully you're with me on that. Like, I'm saying that the way to make a wave, the way nature makes a wave, is it lines up a bunch of harmonic oscillators and staggers the oscillators in phase by a constant amount. That's why the phase constant is so important, because it's what's driving this whole thing. So at any given moment, height, if you say like how high is the thing, height is now a function of two variables. If you say how high is the thing, I've got to tell you when I'm looking and where I'm looking to know what I mean by height. So this becomes a wave. And that's why K is known as the wave number. Without K, we just have an oscillator. With K, we now have a wave. So K is known as the angular. It's angular because it's still measured in radians, but it's wave number because so K, like it says in the videos, K is to space as omega is to time. Omega is how quickly you're going back and forth in time, how any individual oscillator is going, and I will expand more on this on Wednesday, of course. But omega is, and ask me more questions on Wednesday, but omega is how rapidly something is cycling, one individual oscillator is going up and down. K is how many cycles, how many full wavelengths. Oh, maybe, there was a question. Oh, sorry. Sorry. Yes. Oh, sorry. Yes. Okay, beautiful. Sorry. Well, I'll finish it. K is exactly what Raymond's saying in the chat. That's perfect. Yes. And I can't even say it any better. So if that works for you, great. Maybe I'll try to expand that more Wednesday. But he's exactly right. If you were to make a graph of phi as a function of x, then K is the slope of that graph. That's perfect. Yes. Awesome. So it's a constant just like omega. It's cycling rate per space rather than cycling rate per time. Very quickly, then I'm going to say, just like omega is the number of cycles per every unit of time, and a period is of one cycle, then K is the number of cycles for every unit of space, which you know from other science classes is called the wavelength. Right? The units of lambda wavelength are not seconds per cycle, but meters per cycle. Just like period is seconds per cycle. Now I know the bell's about to ring. The bell. Okay, I'm not going to do this now because I know class is about to be over where I'm going to pick up on this, but just so you know where this is heading, the next thing this is now a solution. This new equation that has two independent variables in it. It's no longer an oscillator. It's now a wave. Is it the wave equation? Hold on one second. Yes, I thought someone else asked this in direct chat. Yes, in lab 3, you can start discussing waves in your post lab. Yes, in lab 3, yes. So let me just, I know it's 4:20, let me just say this. I won't write anymore, and you can hang out for a second if you want to ask questions, but let me just say, this thing right here, it's not the wave equation, it's a solution. If you differentiated it twice with respect to time, and then differentiated it twice with respect to space, put those things together, you get the second order differential equation for waves. In other words, and I will do this Wednesday, right? But you did it in lab in theory. But just so you understand, we had a differential equation that dictated simple harmonic motion, and its solution was just a cosine omega t. But now we have a t and an x. If we differentiate this twice, we get a new differential equation. It's the differential equation that describes waves, and it's from that all the Doppler effect and all that stuff comes. So we'll do that Wednesday. But that's where we are now. I hope this clarified a little bit, or at least told you what you need to know for right now. Anyway, so I will hang up, but we're done. You can leave. I'll see you Wednesday. Thank you for being so patient. I'm going to turn off the recording, but if there's any questions right now, I'm here. Okay, but thank you for your patience.